let's take a look at this example right here. Let's consider an average helium atom at room temperature. Let's say we put that helium atom in a 1-meter box. Okay? And let's look at the allowed energies for that. Let's look at the average helium atom. Kinetic molecular theory, okay, predicts that the average energy is 1/2 kT. K here is Boltzmann's constant, and so that's equal to your gas constant divided by Avogadro's number. Okay, you could just memorize that number, but I'd rather just memorize, since I've already memorized the value for R and Avogadro's number, I'd rather do it this way. It's 8.314 joules per Kelvin per mole. Avogadro's number is 6.022 times 10 to the 23rd per mole. So what do we get now? Per mole cancels out. So Boltzmann's constant is 1.38 times 10 to, let me see, just bring up math again. Where's math soft? So you have 8.314 divided by 6.022 times 10 to the 23rd. Oops, 0. Okay, let me set my zero tolerance here to 300. Okay, so it's 1.38 times 10 to the negative 23. Okay. So 1.38 times 10 to the negative 23rd joules per Kelvin. So what's the average kinetic energy of a helium atom at room temperature? 1/2 kT, assuming it's moving only in one dimension. 1/2 times 1.38 times 10 to the negative 23 joules per Kelvin. What's typical room temperature? Which is 298 Kelvin, typical room temperature. And what would that be? Let's see. So K equals 1.381 times 10 to the negative 23 joules per Kelvin. Temperature is 298 Kelvin, so 1/2 of K times T equals 2.05 times 10 to the negative 21 joules. 2.058. So 2.058 times 10 to the negative 21 joules. All right. What's N for that? So let's say that's the energy of your helium atom. So that's going to be equal to N squared H squared over 8m L squared, right? And we have a 1-meter box, so L is 1 meter. We know the value for H. We know the mass of helium. What's the mass of helium? Let's just say 4.00 atomic mass units. You have to change that to kilograms. So let's to quickly solve for that. Let's put it in MathCAD. So we can say E equals N squared times H squared over 8 times the mass times L squared, right? If I want to solve for N, I just highlight the N right there, go to symbolics, solve for the variable, and that's the expression right there. You can see N squared. It gives you two possible values for N, a positive and a negative value, because you have an N squared there. Right? So let's just solve for, put that as your N. N equals that. Right? And what did we say our energy was? 1/2 kT. So we now know our energy. Let's define our mass. Mass is 4.00 atomic mass units. And what's an atomic mass unit? 1.67 times 10 to the negative 31. Oh, no, I'm sorry. 10 to the negative 27? 26 kilogram. And H is Planck's constant, 6.626 times 10 to the negative 34 joule times seconds. So we get an N equal to 1.53. Okay. It should be unitless, right? Oh, we haven't defined L, that's why. L equals 1 meter. There. Okay, so it's 1.58 times 10 to the 10th. So that's what? 15 billion, right? So imagine you have a 1 meter box, okay? And the wave function for that helium atom has N equals 15 billion. How many nodes are you going to have within that 1 meter box? You divide that 1 meter length into 15 billion segments. And what do you think is going to happen? So you have a 1 meter box. From 0 to L. You're going to have 15 billion nodes here for your psi. So you have 15 billion cycles there. What do you think then, if I were to just ask you, how would you describe the probability of finding the particle in the box? It's pretty much constant throughout the box, right? The wavelength, you say, the de Broglie wavelength, in fact, is just the wavelength of that sine wave, is very small. That's very, very small wavelength. So you're approaching the classical limit. Anytime you get to very short wavelengths, okay, you won't see quantum effects. So for practical purposes, a helium atom in a 1 meter box, you can treat that using classical mechanics. Okay, so there's equal probability of finding it everywhere in the box. If you like a third of the box, if you pick a third of the box, the probability of finding it within that third of the box is going to be 1/3. If you took half the box or a tenth of the box, let's say, then the probability of finding it within that 1/10 of the box is going to be 1.1. So you are approaching the classical limit.